Hey everybody, Dr. A here, and in this video we're going to be providing some background information on virtual work for beams and frames. Now remember, beams and frames collectively are sometimes called what? Flexure systems, okay? So this is for flexure systems. Now we're going to find that the virtual work process for beams and frames is going to be a bit similar to what we saw when we learned about virtual work with trusses in one of our other videos. So you can always go back and look at what we did there and kind of compare the two because they are the same type of method, just a different structural system now, okay? So like we've studied before, virtual work is an energy-based method used to compute deflections, which we call delta, or slope angles, which we call theta, at a point on a beam or a frame, okay? Now, again, we learned how to do this when we want to calculate a joint displacement in a truss. Now we're tackling beams and frames with the same type of method, okay? So what do? Well, we place a virtual unit load at the point of interest in the expected direction of deformation. We've seen this concept before with trusses. If we want to compute a deflection, delta, we place a unit force of 1 in the expected direction of displacement at the point of interest, okay? Now, what if we want to compute a rotation angle theta? Well, we place a unit moment of 1 to compute theta, okay? And then from there, we do method of sections twice, okay? We use method of sections on the real system to get the real internal moment functions, which are capital M. And then we do method of sections another time on the virtual system to get the virtual internal moment functions, little m, okay? So again, have we seen this process before? Definitely. We saw it with trusses. With trusses, we had to do method of joints 2 times. Once to get the virtual member forces little f, and then again to get the real forces capital F. So similar things, except now we're getting these moment functions, okay? Now we're going to have to do this, use this method of sections, and make however many cuts are necessary based on the specific problem we have, okay? So let's turn the page here. At the very end, we're going to apply the virtual work formula, whichever version of the formula we need, either to get a displacement or a deflection delta or a rotation angle theta, okay? So here is how this comes out. If we want a deflection delta, okay? So for deflection delta, here's what happens. We say 1 times delta equals the summation as I goes from 1 to n of the integral from 0 to L, little m, capital M, over EI dx sub I. Now, if we want a rotation angle, we say 1 times theta equals the summation as I goes from 1 to n. Same basic formula, 0 to L, little m, capital M, over EI dx sub I, okay? Now, the difference here is, remember, if you want to calculate a capital delta, these moment functions come from what? Putting a unit force on the system, whereas if you want a rotation angle theta, this moment function, specifically this little m, comes from placing a unit moment on the system, okay? Now, what do all of these terms mean? Well, we should know this for the most part from our previous knowledge. EI, and I'll put a little sub I, is the flexural rigidity on domain I, okay? N is the number of domains in the system. So what does that mean? That means this is the number of segments after something changes. Remember, when you do method of sections, we typically make a cut section after every abrupt change on the system. Every time you have a geometric change or every time you encounter a new applied load, you have to make another cut section. So N is the number of domains, or really the number of cut sections you're going to end up having for a particular system. And we'll see some examples of this in some follow-up videos. What about L sub I? Notice that we have this L, these L's in the integrals. Well, L sub I is the length of domain I, okay? And then, of course, capital M sub I are the real internal moment functions on domain I, or real internal moment function. I should probably call that a singular because each domain is going to have one real internal moment function, okay? And then what about little m sub I? This is the virtual internal moment function on domain I. Okay, so these are our background information and background formulas for dealing with virtual work as it pertains to Flexure systems. Okay.